Radawan, are you with us now? Radawan?
Yes, I'm here. Hello.
Yeah, okay. How are you? I'm
Good,
Rashid
thank you.
speaking. Yeah.
Hello, Rashid.
Hello. How are you? How is it going in ISC?
Yeah, it's good. It's good. So Corona is, of course, here as everywhere, but it looks good.
Yeah.
How about you?
Yeah, it's same here. I mean, a lot of restrictions, and maybe you might have heard about the recent numbers in Turkey. We have maybe number one in the region in the whole Europe right now.
Okay.
In terms of the number of cases.
Okay.
But we are still working at the university, especially research labs are open. Undergrads are closed, but I mean, trying to work with some restrictions, limitations.
Yeah, but you are doing really an impressive work, like your lab and Kalion, so that's good.
Yeah. I mean, I hope we can reach a good level of excellence soon. But I think we have to wait a little bit because they have some technical problems right now. They are trying to take the people in. Right now I see, okay, they are coming up now. Okay.
Very good.
Is your center open now? I mean, is it?
Yeah, it's open. So we stayed always open, but we have, of course, some restrictions. Yeah, but we are running 24/7 more or less.
Okay. Good. Okay, we can start now. I think with some delay, maybe a few minutes delay. So we start the second session of today's program at Pvcon. It's a great pleasure to introduce to you Dr. Radawan Koppechek. He's a well-known scientist in this field. He was born in Brno, Czechoslovakia, former Czechoslovakia. It's now in Slovakia, I guess, Brno.
No, it's Czech.
Is it in Czech Republic?
Yes.
Czechia. Czechia is a new name. So he got his diploma degree in University of Stuttgart in Germany, and also he studied at Portland State University, Oregon, for 1 year, where he obtained master degree. And also towards the end of his studies in Stuttgart, he worked at Max Planck Institute and afterwards at the Institute of Physical Electronics as a research assistant in the field of crystalline silicon PV. He joined Professor Ernst Bucher's group in 1998 for PhD degree, and he completed his PhD in 2002. And until the end of 2006, he did a lot of research and did a lot of projects at University of Constance as a group leader, and focusing on silicon feedstock and development of crystalline silicon tin, silicon films, solar cells. He's one of the founders of ISC Constant. It is one of the major research facilities in Europe on advanced silicon solar cell technologies. He's now working full-time there as a manager and a researcher since January 2007. He's currently head of advanced solar cell department. He's responsible for several European and national research projects that revolve around bifacial photovoltaics and around the development of solar cells, with a focus on N-type devices. Okay, it's a pleasure to give you the stage, Radawan. So please go ahead.
So thank you very much. I will listen to my presentation because it's pre-recorded.
Yeah, it's but you will be with us for any.
Yes, I will be here, of course. Yes.
Okay, thank you very much.
Yes, thank you.
We don't hear any voice, or at least me.
Yeah, I'm not hearing this as well.
You're not hearing that.
Mm-hmm.
Fatih Bey.
Good morning, everyone, and welcome to the
Good.
first session of Advanced Crystalline Silicon Circuits. My name is Radawan Koppechek. I'm the CTO and co-founder of ISC Konstanz. So thank you to the organizer, especially to Rashid, for inviting me to this conference, and also thank you to Kalion for being the gold sponsor. My talk today will be about the power of Perk, and I will look at future technologies, what will happen in PV in the coming years. So here's the abstract. So let me now start with the motivation for this presentation. So there were great news in October 2020 when Fatih Birol from the International Energy Agency announced that PV is the king of the energy markets. And who made it to the king? The Perk technology. So the cell efficiencies are increasing, as you know, the substrate sizes are increasing to, for example, here M6. And that means that actually the power of one solar cell is now at 6 watt. If you go to larger substrates, then even higher. But what is especially astonishing is that the price per watt peak for such a cell is only 10 cents per watt peak. And if you go to the module prices, it's about 18 cents per watt peak. And if you implement such modules, and even if you make them bifacial, then you can generate a lot of energy. And the LCOE for such systems are these days between 1 to 3 cents per kilowatt hour, which makes it really the king of the energy markets. The question now is, what will make it the emperor of the energy markets? Because with the crystalline silicon technology, I would say we are not at the end, because still we can reach higher efficiencies and lower costs. And to our understanding is that the emperor will be a simple IBC concept based on the Perk technology. And this means that if you go to IBC, you can have different structures for IBC. So for example, floating emitter or FSF. But anyhow, an IBC, poly IBC or silicon heterojunction IBC can make it to a very high efficient solar cell, reaching 25%. And if you go to M10, so you have already 10 watt from one wafer. And of course, it has to be cost effective, but this is what everybody is now working on. And it can be also on P-type wafers, because now P-type wafers are becoming now with better quality. However, I'm a big fan of N-type, because N-type still has some advantages. So already my conclusion at the beginning is that PV will become an IBC market, and that's because it's much easier to implement polysilicon or let's say also heterojunction technology on an IBC concept. So anyhow, I started with the conclusion, but coming to the outline, what made PV the king of the energy markets, I will explain this in more detail. Then I will talk about the powerful Perk technology. Then focus on future technologies like IBC, polypert, silicon heterojunction, and so on. And at the end, I will of course come to summary and an outlook. So we come now to the history of photovoltaics from 1995, and there is a famous saying of Mahatma Gandhi: first they ignore you, then they laugh at you, then they fight you, and then you win. And this is perfectly the situation in PV at the moment. We are winning because we are the king of the energy markets, but actually we started with very high cost for the modules, even higher than $5 per watt peak. So actually the creation of the market was very important. In Germany, we created the feed-in tariff, and then the module costs were down. And what was very important is also the mass production in China. And so it happened that with an evolutionary process, we achieved costs now for modules at 20 cents per watt peak, and they are still decreased. And we believe that the limit will be something at 10 cents per watt peak. But of course, we know that we will install in few years terawatt systems. And actually, what was needed was the feed-in tariff, then mass production, and now new technologies are entering the market. Now coming to the technologies, and we can see that crystalline silicon is now the winner. In this graph, you can see the areas that were predicted by Martin Green, and many people believed actually that crystalline silicon will come to a limit, and then thin film has to kick in, and then maybe a third generation like hot carriers or quantum dots. But actually very soon we could already see that crystalline silicon is more powerful as expected. In 2020 we are already in the region of predicted of the Tandem Technologies, and what will happen in future is quite obvious, that crystalline silicon will be lower cost and more efficient. And in the next 5 to 10 years we will be dealing with improving the material quality, passivation, improving the junction, and also, let's say, implementing passivating contacts. And then the question is, what will happen if we reach this theoretical limit of crystalline silicon? Maybe there will be implementation of Tandem Technologies, which are crystalline silicon based. So crystalline silicon will be the bottom cell, and for example, the most famous candidate at the moment are perovskite that could be put as a top cell on the device. So crystalline silicon is the winner. In 5 to 10 years, we will work on crystalline silicon upgrades. And the question is if crystalline silicon-based tandem technologies are to come. So let us now look at the crystalline silicon technologies. Couple of years back, from 1995 to 1915, so 20 years, that was quite simple. The question was, should I go for lower cost multi, or will I buy a little bit higher cost monocrystalline modules? But now the situation is completely different, because from 2016 on, there were Schottky, very low cost wafers available. So the development of the cell geometry continued quite quickly. So at the moment we have a very powerful P-type Perk on the market. And the question now is when there will be a switch to PERT or TOPCon or heterojunction and IBC. And this multicrystalline silicon is now gone, because we need more powerful modules for the minimizing the levelized cost of electricity. PERK became #1, and the question is when N-type will come with more impact into the market. So what is happening also now, and I told you before that in 2016 the company was actually Longi who put this cost-effective wafers, CZ wafers, on the market. And then we had a huge mass production of PERK. So the world switched from one time very fast to the other to Perk Technology. I will show one graph later. And the machines are now produced with a much higher throughput, and the wafer sizes are increased, so you have even more, even higher throughput. And so what is happening at the moment is that in 2095 the wafer size was 10 by 10, and now it's rather going towards M6 or even M12, which is 210 times 210 millimeters. What happened is the increase of wafer size, of course, then the solar cell power, and also number of bus bars. And if you look at it in this graph and also think into the future, so in 2015 we had still this 156 times 156, which is M0 Perk solar cell. After that, now in 2020, I would say the minimum size is now M6 Perk with many bus bars, and of course because the cells are getting larger, are getting more and more interesting, because the perfect size of a cell or the structure, it's not a square, it's a long and shallow wafer. Will happen also in future, then maybe 2022 the standard will be M10 or M12 even, with even more bus bars, and then also moving to Topcon with passivating contacts, depending on when the polysilicon will be available on the market. The final, the holy grail is IBC with also polysilicon implemented on the rear side, let's say with 25%. So we have then N-type as the winner rear contact, and half or even shallower solar cells. On this slide you can see our Zebra module, which looks like already like a future module. We have IBC cells made by SPIC and sold at the European market by Futurasan. So we have G1 160 half cell modules with 21.3% efficiency. And then depending on how large the wafer substrates will be in future, we can imagine also that we will have shallow and very long stripes. Like you can see on this slide, so nobody knows what will be the biggest sizes for the wafers. So we could produce also very large wafers and have it in stripes. I don't believe that there will be only, let's say, one long stripe, but let's say 2 or 3, it's possible. And then we can end up with very high efficiencies and low costs for the modules. So, N-type, rear contact, and long stripes are the future. On this slide you can see a typical roadmap that actually every company is having in a similar form, depending on how optimistic the companies are on tandems. Sooner or later the tandem technology can kick in. So in the terminology of Meyer Burger, we have, let's say, the 4G technology is like without passivating contacts and heterojunction contacts. Then polysilicon is then kicking in, or heterojunction structures, and 6G is then the tandem concept. So at the beginning, now almost everybody is still with the PERK concept, but then maybe switching to NPERT or IBC, and then sooner or later there will be also tandem concepts out there which can go above 28% in production. N-type will have something like 24 plus on cell level, then adding rear contacts 25 plus, and then crystallized silicon Tandem Technologies could have even efficiency above 28%. And this you can see also in the roadmap of Meyer Burger. First they have the standard H-pattern technology, they have the plan to switch to IBC to reach higher efficiencies in the modules, and then later sooner or later they will go to tandems with Oxford PV. So now coming to the Perk technology and to the power of Perk. A Perk is a very interesting structure that you have on the rear side not fully aluminum back surface field, but some points that are grooved by a laser during the opening of the silicon nitride. And even if PERC was an evolutionary process of aluminum back surface field, it took some while that PERC was established on the market. The bifacial version is also possible with PERC. That means that you are not fully printing the aluminum on the rear side, but printing a grid. And actually the bifacial PERC helped the bifacial photovoltaics to get unchained. And now in US we will have more than 10 gigawatt bifacial horizontal single axis tracking installations in 2020. So if you want to compare PERC with a standard aluminum back surface field technology that is now washed out of the market because of the low efficiency potential, there are, let's say, only 3 important steps that were implemented on the rear side, which was single side polishing, then deposition of a dielectric, which is now mostly aluminum oxide and silicon nitride, which was then opened by laser. And here you can see that actually the rear side looks very much different from the rear side of an aluminum back surface field. That means you were implementing dielectrics with additional hydrogen included, then also depositing or processing dielectric on bare silicon, and the grid was open. So actually the dielectric was also open for some degradation mechanisms. So adding complexity to a system, of course, is also adding the possibility that some degradation, some additional degradation can occur in the system. So when we are adding an additional dielectric, so for example, the hydrogen from the dielectric could penetrate into the system, so we could have additional hydrogen-induced degradation. And if you are opening the rear side, then a probability for potential induced degradation is also there. But I believe that the large PERC producers, especially the tier 1 producers, they are understanding what they are doing, so there is not a big probability that the modules will degrade more in the field. But of course, you should test them. The largest drawback, I would say, of PERC at the moment is that the efficiency is coming to its limits, and in standard PERC you have the possibility to go, let's say, to 680 millivolt or a little bit higher. When you are implementing selective emitters, and you can go to 685 millivolt. And then with the selective polysilicon, which is not very easy, and that's why maybe also IBC concepts on P-type could be interesting. But even if you implement selective polysilicon, then you can reach close to 700 millivolt, but not very much higher. And that's why N-type concepts are getting more and more interesting. On this slide, you can then see how the transition was performed from aluminum back surface field to PERC. So the aluminum back surface field are the blue bars, and PERC the. So since 2016, when LONGi put the low-cost wafers on the market, there was more or less very fast switch to PERC. And now the question is when NPERT or TOPCon or heterojunctions will be so powerful that actually we will observe such a change to N-type. I think that PERC will remain still for a couple of years very powerful, but it can happen that N-types then take over. But the good news is actually that crystalline silicon photovoltaics, it's an upgrade market, and that from one technology you can switch to another with implementing only a couple of pieces of equipment. So we can go to upgrades with implementing laser technologies from standard aluminum back surface field to PERC, then boron diffusion to N-type technologies, and for example implementing another silicon nitride and fast laser ablation already to low-cost IBCs. But let me explain it in a different way with the Lego analogy. So everybody likes playing, everybody likes Lego, and at the beginning we had a very simple aluminum back surface field stone with 20% efficiency, and going to upgrades, you have, let's say, standard stones, much more expensive and complex special stones. And at that time, when going to PERC, it was not clear what aluminum oxide, how it can be used, how deposited, or destruction-free lasers in which pulse the lasers have to work, and also the aluminum paste, what was not quite easy to develop for this purpose. But then it worked, and so at the moment we have a very nice and powerful PERC Lego stone with a efficiency limit of 23%. The question now is which stones to use to make it more powerful, like Topcon-like. Then of course aluminum oxide are already standard stone, boron diffusion using silver contacts. But in order to make it really more powerful and low cost, the special stones are still not matching. So for example, the polysilicon depositions, we still have to find a solution here, or because of the full silver metallization, for example, we have to switch to advanced aluminum paste or looking into copper plating again. But this is what you can also see in this table, that it took quite a long time to select the right deposition and let's say other tools for the PERC technology. At the beginning the question was also, should we use it on multi or mono? Of course there were many multi producers for PERC as well, but then they realized it's easier to go for monocrystalline because the advantage is much higher. Then the question is what to use for passivation, how the alloys deposition should be done, and so on and so on. And we are facing the same challenges with Topcon, but still Topcon is an upgrade of the PERC technology, using N-type substrates, of course, which works better. And then the major question here is what kind of polysilicon to use. LPCVD works, but it's better to have a one-sided deposition and in situ doping, and also really a very fast deposition without breaking the quartz tube. So there are some alternatives, PCVD, APCVD, sputtering, and so on. And also, let's say, the metallization is also one of the challenges, because we are still using silver, so that makes it quite costly. And the question is now how to reduce the silver in there. But of course, at the end, N-type technologies have their advantage. So I believe that actually Topcon, or let's say also IBC, will be the future technology. So I have used Lego stones now to explain you the technologies, but it's also, let's say, good to look at the production facility. So here you can see the cell line for an aluminum back surface field line. These slides were made by Centrotherm. So the wafer is entering in this way and then ends in the IV measurements. And adding a little bit more of equipment, we can come then to a PERC line, like adding lasers and additional silicon nitride machines, but also to NPERT or Topcon. And then even you can go to an IBC line when you are adding boron diffusions and silicon nitride and fast lasers for ablating the silicon nitride for masking and creating the P plus N plus region. So it's possible to produce in the Perk line an IBC line only with the upgrade of the line. So now coming to the IBC technology as the holy grail. There are many modules in the market, and here you see the summary of Taiyang news about the module efficiency. So Perk is getting very powerful, very close to 21% efficiency. But on your left, you have, of course, IBC and heterojunctions. So the modules with the highest power have the contacts on the rear side, and when the cost of ownership is good enough, then this is the future. And if you put our Zebra technology in these bars, we are at 21.3% efficiency. So now coming to the complexity of different IBC processes. So we have Zebra and Jollywood, which are, let's say, IBC cells in 4G. And then we have LG Electronics and SunPower already using passivating contacts. So Zebra is 80 to 90% similar to the Perk technology. The Jollywood cell 80%, and because LG Electronics and SunPower, they have slightly different processes, it's quite different from Perk. So in our Zebra, we are using PBr3 and silicon nitride, which is different from Perk. Jollywood is still implanting, as I understood. And LG Electronics and SunPower, they have quite complex processes to establish the IBC concept. And the cost of ownership for our Zebra is let's say, lower than 2 times the cost of a Perk, whereas other technologies are rather with a higher cost of ownership. So the major advantage when your process is based on Perk is that if Perk is improving, your cell concepts is improving as well. So if, for example, Perk is now improving the throughput of the machines, we also can benefit with Zebra. At the moment, we are also working on P-type polyperk IBC, because I told you that the substrates are getting gallium doped, so having a longer effective lifetime of the charge carriers, and this could be, let's say, a good step towards IBC concept on P-type as well. So now my final slide about advantages and challenges in N-type. So the advantage is that, of course, you can have high efficiency and low degradation because of no LID, LETID, and for example, also if you take care of potential induced degradation in the module, this can be gone. In addition, you have a higher kilowatt hour per kilowatt peak performance because you have a better low light sensitivity and also high temperature performance because of the higher voltage. And also you can have a very high bifaciality, but the challenges still remain to be as cost effective as Perk. So for example, low cost N-type wafers and still polysilicon deposition if you go for poly IBC, and the major challenge is the silver consumption. So the N-type wafers are becoming lower and lower cost, which is good news. For the polysilicon depositions, people are working on PCVD, APCVD, and PVD tools, and these are improving. And for example, for the silver consumption, you have to go to more bus bar on conductive backsheet, or let's say implement aluminum paste into N-type technologies as well. Now coming to the last point of the presentation, and very quickly I will touch Tandem Technologies, because this will be implemented in production in the coming years, we believe. We We have written an overview about Tandem Photovoltaics, which is crystalline silicon based, and it's now in print at PV International. But when I go to one picture from this publication, you can see that there are 3 different possibilities how to implement semiconductors on top of a crystalline silicon. Now, for example, the hottest candidate are perovskites, so I made a picture here with perovskites on top. It's in the 2-terminal approach, 3 or 4-terminal. So 2-terminal means that you have 2 contacts out of the module. Then 3-terminal, if you are using an IBC cell, you can then have 3 contacts, or you can have then more or less 2 independently working modules, which is then the 4-terminal concept. And for 2-terminal, this is what Meyer Burger and Oxford PV are working on. For example, the heterojunction technology is very promising, or you can use Topcon at the bottom, or you can use for 3-terminal IBC concept. And for the 4-terminal, it's very good to have a very low-cost cell underneath the perovskite, so PERC or NPERT could be interesting. And monofacial could be interesting for rooftop, but let's say if you go for utility scale, you have to go for bifacial tandem technologies as well. And we are organizing a tandem PV workshop. We organized already one this year, so you can download the 3 presentations that are actually the content of the publication. And then our new workshop will be in Berlin in 2021 in April. I come now to the conclusion that PERC is a very powerful technology that made photovoltaic the king of the new energy, but PERC is now coming to its limits at 23%. So we believe actually that N-type technologies will gain momentum and will be the emperors of energy markets. And the winner is IBC technology. And maybe then later the tandem technologies will be more and more visible on the market. So with this slide, I'm at the end, and thank you very much for your attention. And I would like to invite you to the Tandem workshop in Berlin in April 2021. And this workshop is then followed by Silicon PV and NPV workshop in Hamelin, but we will make it also a virtual conference. So thank you very much for your attention.
Okay, thank you, Radawan, for this very nice recorded presentation and giving us a general view of the, and then also for the future of crystal silicon technologies. We have a couple of questions that reached to me. Just a minute. One of them is, can you compare the adaptability of Topcon and IBC to standard fabrication? I mean, you have a PERC line and you want to invest on the next generation technologies. Which one is better suited for this upgrade, Topcon or IBC?
Yes, so I
IBC design is critical. I mean, it depends on how you fabricate IBC, but from your perspective, which one is preferred? Yeah, go ahead.
Yes, I think the holy grail is actually a combination of both, of course. It's a poly IBC or heterojunction IBC, what Meyer Burger will go. But I believe that at the moment still, because polysilicon is not very cost effective, and so many producers in China are using LPCVD furnace, but that's not the solution because there are many drawbacks. So I would say as soon as the PCVD, APCVD polysilicon depositions are ready, I would go for Topcon. But now the intermediate step would be IBC solar cells without passivating contacts. Of course, let's say LG Electronics and SunPower, they have a very powerful IBCs, which are very, let's say, useful for rooftop applications. But what I'm talking now is more or less to a technology that could replace PERC, and that's a PERC-based IBC technology. First step, I would go without passivating contacts because the machines, let's say, are not ready, and then to poly IBC as a second step.
Okay, thank you. I have a question regarding this VOC values of PERC cells. You have mentioned about 685 milliwatt. Is this the value? Is this the value you obtain after stabilization? Is this the stable value that you reached at cell level of these structures?
Exactly, it's the value after stabilization. Yes, and
I mean, is this LETID problem, this elevated temperature degradation, is this fully understood and solved by the industry, do you think?
It's not fully understood, but you have indications that I mean, LETID is a combination of many degradations. It's like even LID included, but let's say the major drawback for PERC is the hydrogen induced degradation, and that means that the hydrogen, normally I learned in PV class that hydrogen is good for cells because they are passivating the impurities, dislocations, but it can be also bad. And if you can manage the process that you are not releasing, let's say, too much hydrogen into your material, or if your material is dislocation and impurity free, you can make a LETID stable solar cells. So no stabilization is needed at the end, but of course, yes, many PERC producers are still working with the stabilization process, but LETID can also occur in N-type if you are not doing a very well process control.
See, okay. Okay, Radawan, thank you very much for being with us today, and I hope we meet face to face soon.
Yes, and thank you, Rashid, for the
other
invitation again.
Locations, yeah, and hopefully maybe in Silicon PV, but Silicon PV will be online. Actually,
it will be online, yes.
Be online, and maybe PVSec, we see. So depending on this COVID restrictions, so we get together, and I hope you visit us and also visit Kalyon facility here. I know that you are collaborating with them, and also maybe we can create some collaboration between ISC and in the future.
Yes,
okay. Thank you again.
Perfect.
Thank you very much.
And keep up the good work. You are doing a very good job in Turkey. Thank you very much.
Thank you very much. Bye bye. Bye bye. Okay, our next speaker will be keynote speaker will be Hisham Nasser. Hisham is from our center. He got his degree from physics department of Middle East Technical University, and he received his PhD again from METU, from Micro and Nanotechnology Graduate Program. He conducted his PhD at UNAM facilities, and he worked on hybrid photonic and plasmonic interfaces for thin film silicon solar cell. And he joined UNAM as a research scientist in 2015. His main research interest has been the development of novel light trapping schemes to enhance the photovoltaic performance of silicon solar cells, and also to optimize the position material property relations of ALD grown ultra-thin layers, and then also passivation of developed novel passivating and dopant-free carrier selective contacts for high efficiency solar cell. He has published more than 20 papers and then made a lot of conference presentations. He is now coordinating the national project supported by TÜBİTAK, where he aims to develop complete dopant-free silicon heterojunction solar cells. He's part of several national and international projects that are being run at GUNAM facilities. So Hisham, please go ahead with your presentation. The stage is yours.
So can you hear me?
Yes, we hear you.
So thank you for the nice introduction. And my presentation is pre-recorded. So
Okay.
I'll be with you. Anyway.
Yeah, okay.
So first of all, I would like to thank everyone for being here and hope that everybody is enjoying good health. And thank the organizers for giving me this opportunity to present our results on one of the recent emerging technologies in silicon photovoltaics, the dopant-free carrier selective contacts, which are some of them are able to passivate the crystalline silicon surface and have the potential to attain high efficiency from the solar cell. And I am from the Center for Solar Energy Research and Application, GUNAM, of the Middle East Technical University. And today I will give some key results related to dopant-free and passivated contacts for solar cell. So this is the outline of my talk. After a short introduction and motivation, I will describe the concept of dopant-free and passivating contact solar cell, and then I will give some of our results on molybdenum oxide applied to the rear side of industrial scale P-type solar cell, as well as on PERC and silicon hetero junction with intrinsic amorphous silicon as passivation. And then I will summarize some of our results on titanium dioxide being used as an electron selective layer, and also their application to solar cells. And I will end with a few conclusions. But as you might know, standard solar cell or most conventional solar cell consists of a simple p-n junction formed by phosphorus diffusion on the front side of a p-type wafer. The back side usually is formed by depositing aluminum film, followed by high temperature screen printing to form a P+ back surface field. This is why these type of solar cell are called aluminum back surface field. In this device, electrons are collected by front side at the p-n at the junction front side, while holes are collected by the back side aluminum contact. So far, the best efficiency has been slightly above 20% from this solar cell, and some of the drawbacks of this device are high recombination rate at the rear side, as well as this solar cell suffers from severe parasitic light absorption at the back junction. And until few years back, this technology dominated the commercial PV market in the world. An alternative and successful solar cell is the aluminum back surface field is the passivated emitter rear contact solar cell, or PERC, which is also fabricated on P-type wafer. The front side is formed by phosphorus diffusion, and the rear side is passivated usually by atomic layer deposited aluminum oxide, which is followed by capping by silicon nitride. The rear contact is local with only few percent of opening, followed by aluminum screen printing to form local aluminum back surface field here. And this cell demonstrated higher efficiencies, well above 22%, because of this cell can have improved short circuit current density thanks to the optimized back reflector by aluminum oxide and silicon nitride. It has also improved VOC because now the aluminum back surface field is local and most of the rear side is being passivated. And now it's currently the dominant PV market, dominated the PV market right now, this back surface field, this PERK technology. The most common feature that limits the efficiency of aluminum back surface field and PERK is the direct application of metal with silicon. And this metal silicon contact leads to lots of recombination losses of electrons and hole, because there is a high density of active state at this interface. And this state usually lie within the band gap of silicon. Well, the use of aluminum back surface field or boron doping can reduce this effect. The Schottky hole resistivity, this high doping, but still doping the absorber, silicon absorption, it has its own fundamental limitations, such as OG recombination, band gap narrowing, and free carrier absorption, which limits the overall device performance. To remove these limitations, so-called passivating contact are being developed recently, which can further reduce the contact recombination losses, as you can insert a passivation layer between the silicon absorber and the overlayer metal terminal. So this, you can think of a solar cell as a balloon which is filled with photogenerated electron and hole. These electrons and hole need to have a skin that confine them within the silicon so that their number and their energy become as high as positive. And this skin can passivate the defects, so you reduce the recombination at the interface. You can form this skin by applying some passivation like silicon dioxide, intrinsic amorphous silicon, aluminum oxide, make some doping, or apply some material with different work function. However, you need to extract this electron hole in a solar cell. And you need metal contact for that. And when this contact structure, metal contact structure, with different dielectric, if it can passivate the silicon surface and selectively extract one type of the carrier, we are forming what's called the passivating contact. So passivating contact technology remove the dopant from absorbent material together with, I mean, you don't need to make doping of the wafer, and you can put these, the electron and hole collecting layer on the wafer itself. An excellent example of this passivated contact solar cell is just the silicon heterojunction, which is passivated by intrinsic amorphous silicon, and the silicon wafer is not processed at all, and carrier selectivity are formed by doped amorphous silicon P and N type, which are placed one at the front side and one at the back side. You need some transparent conductive oxide to collect the charge carrier. And heterojunction solar cell have been very successful in terms of conversion efficiency, efficiencies above 25% are possible. However, in industry, manufacturing has been limited due to some technical difficulties. You need good control on the amorphous silicon layer, especially the intrinsic and P type on the front side. And to deposit this material, you require really toxic material, which necessitates additional investments, which also increase the cost. Apart from fabrication complexities, this solar cell is known to have some parasitic light absorption on the front side because P-type amorphous silicon has very low band gap. On the other hand, in principle, you don't need doping to form a solar cell. So if you find a material here which can collect electrons and the material here which collect holes, you can make a dopant-free solar cell. And this type of material, which are selective to one layer, to one carrier, either hole or electrons, have been the focus of many investigations in the recent years. There are many materials proposed for this purpose, such as metal fluoride like lithium fluoride, potassium fluoride, magnesium fluoride, and metal oxide like molybdenum oxide, titanium dioxide. And this material can place one, for example, this is the hole collecting layer placed at the front side. This is the electron collecting layer, which is on the back side. In some cases, especially for molybdenum oxide, you might need some passivation layer. So if we look closer at titanium dioxide, we see that titanium dioxide form small band, small conduction band offset, so electron can tunnel and reach the contact, while there is a large valence band offset, so holes are reflected away. On the other hand, molybdenum oxide, with its high work function, which can well above 5.5 electron volt, and in general, when this material is, and any material with high work function is applied to N-type silicon here, accumulation of holes or repulsion of electrons occurs at the interface. The holes in the inversion layer can now tunnel to the conduction band of molybdenum oxide layer, and electrons are repelled away by the potential barrier formed here at the barrier. Well, of course, here for molybdenum oxide, the work function is a critical parameter. So if you have a very high work function in connection with silicon, accumulation of holes is observed. So these parameters are critical, and the work function are usually depending on the material properties. So in order to further understand the effect of this work function on the device properties, we carried out some device simulation using cell vacuum tools for this structure here. For this structure, we placed molybdenum oxide on the front side, and the back side is composed of intrinsic and amorphous silicon. And the interface here is also passivated with intrinsic amorphous silicon. We use amorphous silicon, intrinsic, and doped N-type because the material properties are known, so we can isolate the effect of molybdenum oxide and its work function on the overall device. We have found that the solar cell parameters are very sensitive to the work function of molybdenum oxide. And we have found that the cell efficiency increases with increasing that value. By the way, this is the theoretical limit of the work function of molybdenum oxide. And with this structure, simulation show that high efficiency of above 25% are possible. And I invite you to listen to a presentation about this work by Dr. Haris Mahmoud later today. So with this motivation, we studied molybdenum oxide experimentally. But before we proceed into solar cell results, we first try to understand experimentally the nature of the junction here. So the nature of this junction between N-type silicon and molybdenum oxide. That junction is formed between high work function molybdenum oxide and silicon. So we need to understand the transport mechanism between silicon and molybdenum oxide. And we try to answer this question: is the junction act as conventional p-n junction or a Schottky junction? And in order to answer this question, we prepared two simple solar cell structure, with the front side being on N-type wafer. So we dope the front side after texturing to create front surface field, and molybdenum oxide is now placed at the back side between aluminum and silicon. So in this study, we didn't intend to achieve solar cell with high efficiency, as you can see from the device structure, as it has no anti-reflection coating and proper passivation on the front side. For molybdenum oxide, we used thermal evaporation at room temperature to deposit 10 and 15 nanometer of molybdenum oxide. And in order to identify the nature of the junction, we used two wafers to produce these devices. This wafer has different phase resistivity, one with 1 to 15 and one with 5.5 to 15. So we have two wafers, one lightly doped and the other is moderately doped wafer. And here are the obtained photovoltaic characteristics from molybdenum oxide back junction solar cell. This is with moderately doped wafer. This one is with moderately doped wafer, and this is with relatively higher doping concentration. The solar cell with lightly doped wafer resulted in higher conversion efficiency, while the cell with higher doped wafer resulted in degraded PV performance. For the cell with moderately doped wafer, as you can see here, molybdenum oxide free device. So the device without molybdenum oxide resulted in very low efficiency. This result was expected because silicon aluminum Schottky junction cannot effectively separate carriers, as well as there is the presence of high defect density at this interface. Now, placing molybdenum oxide between aluminum and silicon improves the efficiency, and an efficiency of almost 12% is possible with this simple device. For 10 nanometer, we didn't get a good efficiency because 10 nanometer was not enough to fully cover the silicon surface, so resulting in some local places where aluminum is touching silicon, as can be seen from the low VOC. Now, if we look at the device which was prepared with a highly doped wafer, we see that the device without molybdenum oxide here, so just we have silicon, didn't show any diode behavior, because when we increase the doping concentration, it results in a thin depletion layer width between aluminum and silicon, across which generated electrons and hole can tunnel, which result in a rather ohmic behavior here. Now, after inserting molybdenum oxide both with 10 and 15 nanometer between aluminum and silicon, it didn't lead much enhancement in VOC. So we have the highest 310 millivolt, and the overall performance is very low compared to the cell which was prepared on lightly doped wafer. So far, molybdenum oxide on lightly doped wafer resulted in higher VOC and thus higher efficiency compared to this device with molybdenum oxide on highly doped wafer. So if you look at the general diode equation here under illumination, and at this condition, open circuit voltage is given by this expression. So for p-n junction, J0 is given by the following expression, which depends on the diffusivity, diffusion length, and the carrier concentrations respectively. So now when we increase ND, the carrier concentration, as we did, J0 should decrease, and VOC is expecting to increase. However, in our case, we observed the opposite. So when we increase ND here, the doping concentration of the wafer, by using highly doped wafer, VOC decreases. So p-n junction model fails to explain the junction formed between molybdenum oxide and N-type silicon. So on the other hand, this is the Schottky junction model. G0 is given by this expression, where the barrier height is given by this expression. It's related to the work function of molybdenum oxide, the silicon electron affinity, and the Schottky barrier lowering, which is proportional to fourth root of doping concentration. Now, when we increase the doping concentration of silicon, this results in increase in barrier lowering, and the barrier height decreases, which result in decrease in VOC. And this is what we observed experimentally, that increasing ND resulted in decrease in VOC. So this observed degraded cell performance with increasing crystal silicon doping concentration suggests that transport mechanism at N-silicon and molybdenum oxide junction is governed by Schottky barrier thermionic emission of majority carrier, and not by diffusion of minority carrier. Now, with increasing the N-silicon doping concentration, the Schottky barrier width itself for conduction band edges between molybdenum oxide and N-silicon reduces, and now electron can tunnel and reach the aluminum contact, and the whole selective capacity of molybdenum oxide reduces. In here, we applied whole selective molybdenum oxide in large area bifacial silicon heterojunction solar cell. The N-type wafer is passivated with intrinsic amorphous silicon on both sides. The back surface field is formed by N plus amorphous silicon followed by TCO. The front side, we have passivation with intrinsic layer followed by whole selective thermal evaporated molybdenum oxide, and then covered by ITO and low temperature screen printing and low temperature firing. Now, molybdenum oxide itself has a wide band gap exceeding 3.3 electron volt as measured by ellipsometry, and it has low extinction coefficient. So we measure high transmittance here, even from 20 nanometer molybdenum oxide. So the transmission is very high over the whole spectrum. This is in line with low extinction coefficient here in red. So indicate that we have low absorption, both in visible and infrared, with more than 90% of weighted, more than 90% above 700 nanometer. Now the solar cell results from this device. So we have dopant-free layer on the front side, passivated with intrinsic layer. We achieved a reasonable high efficiency exceeding 20%, the VOC 694, which basically determined by the excellent passivation of intrinsic layer. GSC is a little bit high, but this overall device is limited by VOC. And details about this study passivation and this fill factor and behavior of the overall cell will be given by Mr. Ergi Donerchak later today. The important point here that I want to say is the excellent EQE response in this portion of the spectrum up to 600 nanometers. So in black, we have the EQE for 20.7% heterojunction solar cell fabricated with almost the same parameters for the backside and the passivation. And the cell attained, the cell with molybdenum oxide has attained higher VOC of 38.8 milliamps compared to 38.44 milliamps. So we have higher GSC, we have higher blue response when we have molybdenum oxide, because molybdenum oxide has higher band gap compared to the amorphous silicon whole collecting layer in the standard heterojunction solar cell. However, on the other hand, according to this report, International Technology Roadmap for Photovoltaics, which was published a few weeks ago, it was found that for 2019, like about 30% of market share is for aluminum back surface field and more than 60% for PERC and the related concept. So when I mean PERC and PERL and TOPCon. And this technology is expecting to dominate the market share for the coming 10 years. On the other hand, silicon heterojunction are expected to gain a share of only 10% in 2024 and 17% by 2030. backside rear contacted solar cell is not expected to gain significant market share, and it's assumed that it changed from 2% in 2019 to only 5% in 2030. Silicon tandem, on the other hand, silicon tandem is expected to appear in mass production after 2022 with low share. So these data highlight that PERC and related technology will be the dominant, at least for the coming 10 years, and usually they are realized on P-type wafer. So this motivates us to study molybdenum oxide, whole selective molybdenum oxide on P-type wafers and then on PERC. So with this motivation, we have applied molybdenum oxide in the fabrication sequence of industrial scale solar cell on P-type monocrystalline silicon wafer. This is the solar cell fabrication, and we have applied molybdenum oxide at the back side here. So we used M2 wafer, M2 Chozraski grown wafer, and we followed this procedure. First, the cell was textured, followed by diffusion on both sides. Then the back side was isolated, was etched, the back doping. Then we applied silicon nitride on the front side, which act as passivation and anti-reflection coating. Then we make 4-pass per screen printing and firing, and the back side was cleaned again, and then we applied molybdenum oxide, followed by silver. And this is the obtained. We also deposited. We also prepared some solar cell without molybdenum oxide as reference. And this is the IV curves of the solar cell, of both the cell with molybdenum oxide silver as rear side passivating dopant-free contact, and then the reference cell. We have higher efficiency with molybdenum oxide with reasonable fill factor. The high fill factor here is an evidence of effective whole transport through molybdenum oxide. However, the overall fill factor is still low, and maybe it can be limited also not only by the backside, but also by front side doping and metallization recipe. So on the other hand, if you look at short circuit current density for solar cell with molybdenum oxide silver, it's quite low and need to be optimized further. And VOC value are in the low, still in the low range of typical passivated contact solar cell, and it can certainly be improved by inserting some passivation layer here between molybdenum oxide and silicon. A more important point here, that is the EQE response in the infrared, where we have our molybdenum oxide and silver contact, especially above 850 nanometer. So we have enhancement in EQE here, which further demonstrate the benefits of using molybdenum oxide at the backside. So we have enhancement in the EQE response in the infrared. So also we checked the surface coverage of molybdenum oxide. So we did EQE mapping at 900 nanometer. So we collected the EQE at fixed wavelength of 900 nanometer, because this wavelength directly reflects the quality of the backside, since light at this wavelength or above can reach the back surface. You can see that the EQE has excellent surface coverage and excellent value, exceeding 78% at this wavelength over different position of the wafer. Only small area here at the corner, the EQE shows between 70 and 72%. This is normal and may arise from slight inhomogeneity in molybdenum oxide thickness across the wafer. Still, this homogeneous EQE response in the infrared confirms adequate conformal surface coverage on texturized back surface of the wafer. So later on, in order to demonstrate the potential limit of the fabricated solar cell P-type wafer with molybdenum oxide at the backside, we performed synergetic efficiency gain analysis, SEGA, using QACA2. Based on this loss analysis, we were able to define the dominant loss mechanism and draw and see how we can improve this, the efficiency from industrial scale P-type solar cell with the real 4-area molybdenum oxide hole collecting rear contact. So as an input in this simulation, we employed different optical, electrical, and passivation characteristic of each layer or each interface of the fabricated solar cell. But first, we need to reproduce the experimental results in a QACA2 simulation tool, as shown here. And both fabricated and simulated IV characteristic of the cell agree well. So this is the experimental result, and this is the simulation result. There are, of course, small deviation, but this small deviation still can assure that this measured value are correct because they were able to generate the experimental data. So this is Sega analysis of our fabricated P-type solar cell with molybdenum oxide silver rear contact. Efficiency gain here are given in absolute %. Well, in Sega in general, when you deactivate individual power loss mechanism by setting its value to ideal value, it gives the corresponding potential efficiency gain. So if you close one loss, you see how much enhancement you are able to get in your efficiency. So this loss analysis show that our solar cell has two dominating loss mechanisms. The one is the one with optical losses of almost 5%. The second one is recombination losses with 2.8%. On the other hand, resistive losses show only 1.25%. Some of these losses can, of course, be avoided or reduced. For example, the dominant resistive loss here is arising from front side finger and pass bar resistance with potential efficiency gain of almost a little bit higher than 1%. This loss can, for example, be reduced by further improving front side metallization or by, for example, using advanced metallization configuration using 5 or 6 pass bars. Also, optimized front side metallization is also expecting to reduce the loss, which is due to front contact resistance, which is still low, but this can also be reduced. The rear contact resistance. So the rear contact resistance, which composed of our molybdenum oxide silver, is the smallest contributor with only 0.1%. And this is expected because we measured very low contact resistivity from molybdenum oxide silver on P-type wafer. Also, the second dominant loss, which arises from recombination, especially at the backside, can be avoided by using a passivation interlayer between molybdenum oxide and silicon, or by further optimizing the front side doping silicon nitride passivation recipe. Most essential here is to avoid optical losses with potential gain of above 5%. And we found that the front and rear reflection is the most dominating individual loss mechanism here with more than 2.6%. So if we look at the total reflection, we see that it is high at shorter wavelength with more than 25%. It's known that this wavelength range is related to front side reflectivity. So it's related to front side texturing and silicon nitride. So one way to reduce this reflection here is, for example, by using double anti-reflection coating, or for example, by using some advanced light trapping interface like inverted pyramid or black silicon, for example. On the other hand, the reflection at longer wavelength is mainly the reflection of the rear side, which is named as escape reflection. And it's also composed not only from the backside, but there is also some contribution of the front side, like external texturing. So external reflection is correlated to front side texturing and anti-reflection coating, and escape reflection is the light which leaves the front side after being absorbed by silicon, interact by the backside, and internal reflection from the backside, where at the backside can be absorbed, can be lost. So in order to further understand what happens at the rear side, we used wafer ray tracer from PV Lighthouse tool. In this tool, it doesn't take into account any recombination or resistive losses of the layer or interfaces. It just predicts the maximum photo-generated current density that we can achieve from our device. And also it can predict how much current is being lost at each layer or interface of the solar cell. So here are the solar cell structure used in this simulation. The front side is similar to the fabricated P-type silicon molybdenum oxide cell, and the rear side feature molybdenum oxide with different thicknesses ranging from 10 to 120. Also, we have simulated solar cells with a reference solar cell with silver or aluminum. Aluminum is just to show the aluminum back surface field. This is the simulated current density, either photo-generated, this one, or the current that's being lost at each interface. But here we are interested in the one on the front side where our molybdenum oxide silver are there. So this is for aluminum back surface field. This is for the solar cell that we produce, and this is for molybdenum oxide with different thicknesses, of course, with silver here. So in brief, we found that a rather thick molybdenum oxide of at least 100 nanometer is required to increase photogenerated current density, which is also coupled with a reduction here with the amount of current that being lost at the back at the back surface. So 100 nanometer or more is required now. This is because dielectric layer with enough thickness, of course weighted with refractive index, is essential to fully block the excitation of surface plasmon polaritons at the back surface. So you are with thick dielectric, you can eliminate the parasitic plasmonic infrared light absorption by the rear metal. However, if you use 100 nanometer molybdenum oxide, you would result, experimentally, you would result in degraded solar cell performance because molybdenum oxide is known to have a high bulk resistivity. So one way to get the maximum benefit is to combine thin molybdenum oxide with low contact resistivity like 10 or 15 or 20 nanometer with other dielectric layers in a similar structure similar to that of Perk. And this is what we did in different study indeed. So yes, we did this study and we combined molybdenum oxide with aluminum oxide and silicon nitride in Perk structure. And we did this experimentally. And you see here now molybdenum oxide now replaces the local aluminum back surface field in standard Perk structure. And we obtained experimentally short circuit current density of more than 39.4 milliamps centimeter square, which is higher than what we get from direct heterojunction between molybdenum oxide and silicon. And for more details about this structure will be presented later today by Ms. Gamze Kokbudak. Now I would like to summarize our results on electron selective titanium dioxide that we prepared by ALD. So in recently, there have been many studies on the use of titanium dioxide as electron selective layer in crystalline silicon. I have summarized them here, some of these key results. So initially, studies were on titanium dioxide on B-type wafer. Titanium dioxide was prepared by MOCVD. It yielded low efficiency. Later on N-type wafer, an efficiency of more than 20%. So titanium dioxide was used as an electron selective layer on N-type wafer, and the efficiency of almost 22% has been demonstrated in literature, and these results are very promising indeed. So one of the important parameters of titanium dioxide is its thickness, and you can see in this study they found that when increasing the thickness of titanium dioxide, the contact resistivity increase. And so this requires a good control over the thickness of titanium dioxide, and this can be done by atomic layer deposition. So only a few, 1 or 2 nanometer change in thickness of titanium dioxide, the contact resistivity increases factor of the device. So ALD itself is, ALD consists of sequential gas solid reaction of two or more materials separated by pairs. And since the chemabsorption of the material required the presence of some active sites on the surface here, the reaction terminates itself once all these active sites are reacted. So ALD process is called self-limited. And indeed, this self-limiting nature of ALD sorry, my BC. Okay, so the ALD process, the self-nature of ALD process provides thickness control at monolayer, and so it is possible to deposit high quality, uniform, and conformal film. So we use this process parameter where TD mat was used as titanium precursor and water as oxidizer. But first we identified the ALD window. Here is the growth, the ALD window where the growth saturate, and we found it between 130 and 150 degrees. At temperature below this window, we have condensation of reactants, and above this window we have loss of species. But as we will see later, the film deposited at high temperature here gives better results. Well, one of the important parameters is the ratio of oxygen to titanium atom in this layer. So it gives you the degree of stoichiometry of the film. And in this study from XPS analysis, we have seen that This ratio is between 1.6 and 1.8, and all deposited titanium films are oxygen deficient. At low temperature here, we see less oxygen because we have condensation of titanium nanocrystal. At high temperature, the dependence of temperature is quite weak, which may be good for the reproducibility of the film. Later on, we studied those titanium dioxide film by CV measurement. As you might know, metal oxide semiconductor structure, as shown here, may provide information about charging states of the layer as well as interface state density. We have fabricated this device on both N-type and P-type wafer, and also we measured CV characteristics, as you can see here, as a function of frequency. This frequency dependence is typical in CV measurement. So if you have interface trap states, or if you have a series resistance effect, or if you have some leakage current in the device, which is typical in such structure. So it's not very easy to model CV data, but we try to understand and extract some information, some information from them. So both CV and conductance results are shown here as a function of frequency, and from this data you can extract the density of states, which is an important parameter in solar cell application. And this can be calculated using the so-called conductance method. Conductance method which is based on a circuit model called parallel conductance. This is very well-known technique indeed for the analysis of oxide structure. And in this technique, in this calculation method, you measure the conductance and convert it into parallel conductance. And by using this model, you plot parallel conductance over frequency. And from that, you can extract the density of state. And this is the density of state that we extract from this analysis. And we have the values here. And as you see that they are in the order of 10 to 12, and this value is more or less similar to what has been reported by others in literature. And in general, we can say that we have more density of state at low temperature grown material, and less density of state at higher temperature grown here. But the lowest DIT is obtained for the film deposited at 230 degrees. So these films are expected to perform better than the other in terms of density of state. And indeed, we used this film, only this film, and we studied the passivation quality of ALD grown titanium dioxide at this temperature. So we used very thin wet chemical oxide, which is about between titanium dioxide and silicon, which is about 1.4 nanometer, and we put titanium dioxide on both sides of N-type wafer. So you see that here the carrier lifetime as a function of thickness of titanium dioxide, and here we compare two conditions. So one with oxide, with chemical oxide, and the other without chemical oxide. So titanium dioxide is directly deposited on N-type wafer, and both scenarios we used forming gas annealing. So as you see here, we have reached very high effective lifetime, which is exceeding 2 milliseconds, which is quite successful. This is obtained with 3.5 nanometer thick titanium dioxide deposited on with chemical grown oxide, followed by forming gas annealing. And this high lifetime translated to a VOC of more than 700 millivolts. So this result proves a promising passivation ability of titanium dioxide for solar cell application. So finally, I come to the conclusion. So molybdenum oxide and titanium dioxide are good candidates for Hall selective and electron selective as Hall and electron selective layer in dopant free and passivating contact solar cell. Our simulation showed that high efficiency is possible with molybdenum oxide, and as we will see later today, also titanium dioxide by later today by other presenters, that titanium dioxide also show high efficiency. We have demonstrated we have also demonstrated large area direct heterojunction, P-type and molybdenum oxide with efficiency of exceeding 17%. And from this, SEGA analysis, loss analysis, we found the main losses arise from passivation, but mostly from rear side optical response. Then we demonstrated more than 19% PERC with molybdenum oxide. And this cell has improved short circuit current density compared to direct molybdenum oxide B-type junction. And indeed, this PERC with molybdenum oxide is the first demonstration in literature using industry feasible processes sequence and tools. Finally, we have also demonstrated above 20% silicon heterojunction with molybdenum oxide as emitter with enhanced short circuit current density in the blue part compared to a reference cell with 20.8 silicon heterojunction. Our cell was unfortunately limited by the fill factor. And for electron selectivity, the tandem dioxide is studied and a very good passivation has been reached and the quite successful lifetime of 2.3 millisecond and 700 implied VOC was demonstrated. Finally, I would like to thank some of master and PhD student and funding from Pvcon. Thank you.
Okay, Dr. Nasser, thank you for your presentation. We are already well behind the schedule, so I will not, we have a couple of questions, but I will pass to the next presenters because of the time limitations. So the next presentation will be made by Ergi Dönerchak. He is a PhD student. He is a senior PhD student, and he's working on heterojunction solar cells at UNAM and fighting a tool, PCVD tool here, and making it a good tool to fabricate silicon-based heterojunction structures. It's not only standard classical heterojunctions he's working on, he's also interested in making heterojunctions with using different materials. Okay, Ergi, please go ahead with your presentation.
Thank you for nice introduction, Professor Turan, and my presentation will be pre-recorded.
Hello everyone, welcome to my presentation on bifacial silicon heterocontact solar cells. My name is Ergi Dönerchak from UNAM, and I'm a PhD candidate at Bifaciality Technical University. I would like to start with well-known based research cell efficiency chart from NREL. As you can see from the chart, efficiency values are increasing year by year for almost all technologies. But in this chart, I would like to focus on silicon solar cell part. So the record efficiency on silicon solar cells belongs to heterojunction IBC structure. The record efficiency achieved by Kaneka with 26.7%. For single crystal solar cells, the record efficiency is 26.1 with Topcon IBC structure. Recent developments show that over 25% efficiencies could be achievable by bifacial silicon heterojunction solar cells with relatively high fill factor values. In the figure, you can see quantum efficiency and 1- reflection results of silicon heterojunction solar cells. The research done by Holman in 2012, and they mainly focused on current loss mechanisms of the silicon heterojunction solar cells. So, on the rare side of the silicon heterojunction solar cell, the current loss is around 0.5 milliampere per centimeter square. And on the front side of the solar cell, the current loss is 2.1 milliampere per centimeter square. Here, for the front side losses of the solar cell, it's possible to use wide bandgap material to decrease parasitic absorption, and also the TCO layer with lower absorptance coefficient can be used. On the rare side, the main loss mechanism belongs to free carrier absorption coming from TCO layer. The main motivation of the study is to decrease parasitic absorption losses by two approaches. The first one is the integration of wide bandgap materials on the front side of the solar cell. The second one is the changing free carrier density of the ITO layer. Here, this is the fabrication process flow of standard silicon heterojunction solar cell. The first step is the texturing and cleaning of the silicon wafers. Then, thin intrinsic amorphous silicon layer deposited on the both sides of the silicon wafer.
An amorphous silicon layer deposited on the rear side of silicon wafer. On the front side, emitter was formed by p-amorphous silicon layer. Then ITO was spotted on the both sides of the silicon wafer. The last step is the metallization. For the metallization, we have used low temperature silver paste. In this video presentation, I will first focus on hydrogen plasma treatment and impact of this hydrogen plasma treatment on interface trap density, hydrogen content, and passivation quality. Then I will inform you about the two wide bandgap materials. One is the molten oxide, another one is the P-type amorphous silicon carbide. After that, I will focus on relation between oxygen partial pressure and the ITO layer and impact of this relation on solar cell parameters. I will briefly explain how we optimize the low temperature silver paste, and I will inform you about the contact resistivity results, and I will finalize my presentation with solar cell parameters. Okay, let's move on. Enhance passivation quality of amorphous silicon layer.
On the left-hand side, you can see the impact of hydrogen dilution ratio on the passivation quality of the amorphous silicon layer. So when you increase the hydrogen dilution ratio, the implied VOC values decreases and effective lifetime values decreases. Up to now, we picked 1/3 hydrogen dilution as the optimum value. Then we insert the hydrogen plasma treatment right after the deposition of the amorphous silicon layer. And for the optimization of the hydrogen plasma treatment, we changed plasma duration, plasma power, and pressure. So the results are given in the tables. On the left-hand side, you can see the implied VOC variation, and on the right-hand side, you can see the lifetime results.
At the end of the optimization set, we have achieved highest implied VOC as a 738 millivolt, and the highest effective lifetime is 3.8 milliseconds.
When we look at the impact of the hydrogen dilution on the hydrogen content, decrease in the hydrogen dilution leads decrease in hydrogen content. And when we look at the changes on interface trap densities, interface trap densities decreases with the increasing hydrogen content. When we look at the overall results, when the silane ratio increased, hydrogen content decreases, interface trap densities decreases, and effective lifetime increases. When we add hydrogen plasma treatment with optimum values, interface trap densities decreases and hydrogen content increases. So with hydrogen plasma treatment, it's possible to bond dangling bonds on the interface, which is resulting lower interface trap density. At this stage, we found the highest effective lifetime as a 3.8 milliseconds. Now I would like to continue with the two wide bandgap material. So let's start with the molten oxide. The molten oxide layer has 3.3 electron volt bandgap value, but itself it has a very high interface defect density, so it is not a proper material to use passivation layer. We have checked molten oxide passivation quality with various thicknesses of amorphous silicon layer. So starting from 3 nanometer up to 7 nanometer, molten oxide enhances passivation quality. But when you look at the passivation quality of the 7 nanometer amorphous silicon, when we add molten oxide on top of it, the passivation quality decreases. As you can see, implied VOC value decreases from 710 millivolt to 700 millivolt.
At this point, we found optimum thickness of amorphous silicon as a 7 nanometer, and we insert this stack layer on the solar cell structure. Let's continue with second wide bandgap material, which is P-type amorphous silicon carbide. For the optimization of P-type amorphous silicon carbide, we have changed methane gas flow deposition power and doping ratio under fixed deposition temperature, silane, and hydrogen flow. I would like to show you conductivity and band gap results of various methane flow and deposition power. So black square results belongs to conductivity and blue circles shows the band gap results. Starting from 10 SCM to 30 SCM. For conductivity results, general trend is decreasing. On the conductivity results, the general trend conductivity value decreases with increasing deposition power, and for band gap values, increasing deposition power leads increasing band gap values. In our optimization set, we could able to increase band gap value of p-type amorphous silicon carbide layer up to 2.3 electron volt. And for these deposition conditions, the activation energy is varying between 0.32 and 0.35 electron volt. In this set, we picked two different deposition conditions in terms of their conductivity and band gap value. Then we insert the silicon heterojunction solar cell structure. Let's continue with enhanced properties of ITO by oxygen partial pressure.
So on the left-hand side, you can see the impact of the oxygen partial pressure on the electrical properties of the ITO layer. So increasing oxygen partial pressure leads increase in resistivity and decrease in carrier density of the layer. However, for mobility, there is an optimum value at 0.6% oxygen partial pressure. Up to that value, the mobility increases, and after that start to decrease. And you can see the mobility and resistivity changes with respect to carrier density on the right-hand side. Band gap decreases with increasing oxygen partial pressure from 3.8 eV to 3.6 eV. When we insert these two ITO layers, one with 0.6 oxygen partial pressure, one without oxygen partial pressure, you can see the quantum efficiency result of the silicon heterojunction solar cell on the right-hand side. On the right-hand side, due to the decrease in the free carrier density of the ITO layer, the spectral response improved and free carrier absorption decreased. In blue region of the spectrum, enhancement is achieved by decrease in the parasitic absorption, but below 340 nanometer, due to the Boostein-Moss shift effect, parasitic absorption increases with respect to decrease in the band gap value of the ITO. Here in the overall, we improved current density by 0.5 mA per centimeter square, only by changing the ITO layer.
Let's continue with the screen printing part. Here we investigate impact of oxygen partial pressure during ITO sputtering on contact resistivity between low temperature past. In this experimental set, we investigate also impact of curing temperature on the contact resistivity results. For all these studies, drying temperature is 110 degrees Celsius. We only change the curing temperature. When you look at the results for the standard ITO sputtering, contact resistivity values are higher than 1 milliohm centimeter square. The results have higher deviation compared to reactive ITO sputtering. So for the reactive ITO sputtering, all contact resistivity results are below 1 milliohm centimeter square. So without reactive ITO sputtering, we achieved higher contact resistivities, and also with reactive ITO sputtering, the deviation on the resistivity values decreased, and we have achieved less temperature dependent performance of the metal contacts. This brings me to solar cell results. Here you can see JV graph of the three different structures. The black one represents standard silicon junction solar cell. On the red one, we have molten oxide on the front side of the solar cell, and on the blue one, we have P-type amorphous silicon carbide. The thicknesses of both emitter layer are 12 nanometer. On the table, you can see the solar cell parameters. So for the standard silicon solar junction solar cell, we have achieved 20.78% efficiency with a relatively high fill factor values. For the structure with molten oxide, we have achieved 20.2% efficiency, but mainly we have faced with series resistance problem on that structure. Due to the series resistance, fill factor decreases to 75.2%. For the p-amorphous silicon carbide, we have achieved 19.7% efficiency. The important point about molten oxide, we could able to improve JSC by 0.4 milliampere per centimeter square. And the source of the main loss on the wide band gap solar cells belongs to relatively higher series resistance. When we look at the comparison of quantum efficiency results, on the front side, below 600 nanometer, we decreased parasitic absorption by molten oxide layer. But above 600 nanometer, losses are increased for molten oxide. And we have achieved almost similar spectral response between p-type amorphous silicon carbide and amorphous silicon layer. This brings me to conclusion. For the passivation of amorphous silicon, we have enhanced the passivation quality by hydrogen plasma treatment, which is resulting lower interface rate density and higher hydrogen content between 300 and 600 nanometer. We could able to improve spectral response by using molten oxide. However, we have achieved higher resistivity values both for molten oxide and p-type amorphous silicon carbide, which is resulting lower fill factor. When we compare the impact of oxygen partial pressure on the electrical and optical properties with oxygen partial pressure, resistivity and mobility values are increased, carrier density, band gap, and contact resistivity values are decreased. In overall results, JSC was improved by 0.5 milliampere per centimeter square. And also specific contact resistivity values are decreased lower than 1 milliohm centimeter square. When we look at the solar cell results, we have achieved record efficiency as 20.8% with standard silicon junction solar cell. For the roadmap, we aim to improve passivation quality of amorphous silicon and decrease parasitic absorption of I2 layer. We will focus on integration of wide bandgap material with more optimal thicknesses to decrease series resistance and to enhance further passivation quality of the amorphous silicon. We will focus on buffer and thin intrinsic amorphous silicon layer. To improve metallization, copper electroplating will be used, and to improve current density, we will work on double anti-reflective coating layer and back reflector coating. Thank you for attending. I would like to thank all authors for their valuable contribution to this work. If you have any questions, I will be happy to answer them.
Ergi, thank you very much for this very nice presentation, and congratulations for the achievements you have made in the last period of your PhD studies. We see the potential of heterojunction solar cells in the crystalline silicon technology. There is one question about the heterojunction materials that you have used, and you have tried molybdenum oxide as a whole selective layer, right? I mean, on the P side of the solar cell. Just to avoid using toxic materials like phosphine and diborane, we need an N-type selective layer on the other side of the heterojunction structure. Is there any candidate for the electron selective layer for your application?
Yeah, thank you for questions. Actually, now we have focused on lithium fluoride aluminum stack, on the rare side of the heterojunction solar cell. And now we are dealing with to decrease contact resistivity without decreasing the passivation of the amorphous silicon. So in our works, we have focused on the lithium fluoride aluminum stack.
I see. Okay. So it's a hard material and a little bit difficult than molybdenum oxide, probably because of the series resistance. You need to use very thin layers of lithium fluoride, and the optimization needs a lot of effort, I think.
Yeah, exactly.
Okay, Agit, thank you very much for your presentation. There seems to be no other questions, so we can now pass to the next presenter, who is Nabil Khelifati. Is from Algeria, from CRTSE, which is Semiconductor Technology Research Center for Energetics, which is in Algeria. It's the major research center on semiconductor science and technology. Nabil has just received PhD, as far as I know. Nabil, are you with us?
Yeah, I hear you.
Okay, very nice to meet you. How are you?
I'm fine. Thank you, Dr. Duran.
So Nabil has received his PhD recently, right? In the last.
Sorry?
You got your PhD last year, right?
Yeah. Last year,
okay. Yeah. And we hope
2090. Okay.
Okay, we hope to work with you in the future, and I hope we can somehow create a collaboration scheme between STE and GUNAM in the near future. So it is a great pleasure to have you here as a speaker. So please go ahead with your presentation. It will be pre-recorded presentation probably again, but we will have the opportunity to ask questions after the presentation. Okay, thank you.
Hello, everybody. Firstly, let me thank you for giving me this opportunity to present part of our research activity carried out in our research center in semiconductors technology for energetic CRTSE of Algiers, Algeria. This talk is on phosphorus and boron co-diffusion in silicon for prepared solar cells application. We note that the work is done in the context of collaboration between our center and the University of Science and Technology Houari Boumediene in Algiers. We start with a brief introduction. As we know, in the photovoltaic market, crystalline silicon wafers based solar cells are the most dominant, with a rate of more than 90%, with the conversion efficiencies exceeding 21.9% and 26.7% for multi and monocrystalline silicon respectively. And this is due to a high energy conversion to manufacturing cost ratio as compared to other materials such as amorphous silicon and CIGS. So the crystalline silicon is used for fabricating solar cells with different architectures such as the conventional aluminum back surface field and other more advanced like PERK, IBC, PERK Plus, and PERT. Among the last advanced cells, we find those manufacturing basing on bifacial technology. We mention in particular PERT bifacial solar cells concept which make the subject of our present study. Bifacial solar cells have several advantages regarding the monofacial ones, as listed here. So the bifacial solar cells have better performance at similar project size, more production at barely higher installation cost, so LCOE reduces. Optimization for projects on which on sites, with high albedo, deserts with suns, and white roof, gravel, etc. Synergy between rear-facing exposure and improved ventilation. Aesthetic interest that used like barriers, canopies, pergolas, brise soleil. So these advantages make bifacial solar cells technology promising and competitive. Context and motivation of this study. As we know, manufacturing of bifacial solar cells requires additional technological steps which increases the cost of their fabrication. In the case of P-type silicon-based passivated emitter rear totally diffused solar cells, PPERT, the creation of the emitters Amorphous and boron back surface field is done respectively in 2 stages. So this increases the thermal budget and as well as increase the cost of delivered power. So among the possible solution to reduce the number of process steps, there is the simultaneous formation of emitter and BSF through the co-diffusion of phosphorus and boron respectively. Well, the main purpose of this work is to elaborate P plus P and plus bifacial structures by the co-diffusion of phosphorus and boron at different temperature on the one hand, and their diagnosis using a set of electrical and optical characterization techniques on the other hand. The samples have been prepared according to the process flow diagram shown here. So the basic material used is P-type monocrystalline silicon with double poly optic wafers. Before any process, the wafers were firstly cleaned chemically in a Piranha H solution, followed by an oxide removing in the diluted HF acid, rinsing in deionized water, and drying in nitrogen flux. After that, phosphorus and boron source layer were respectively deposited on front and rear sides of the wafers using spin coating technique. The spin-on deposit dopant used in our experiments were P509 for phosphorus and B200 for boron, produced by Filmtronics INC. Each deposition is followed by rapid drying in order to partially evaporate the organic species from the emulsion and solidify the layer. After the deposition of the source layers, the wafers are directly introduced into a quartz tube furnace for the co-diffusion of the dopant. The process starts by drying and kneading to totally evaporate the organic species from the source layers. Subsequently, the wafers were subjected to annealing at elevated temperatures to ensure the co-diffusion of phosphorus and boron into the silicon matrix. This co-diffusion process was done in nitrogen ambient and at atmospheric pressure. After the diffusion of phosphorus and boron from the spin coating deposited source layer, the wafers were immersed in a bath containing a concentrated HF acid solution to remove phosphosilicate glass and borosilicate glass. After this, the wafers were rinsed by deionized water and dried. The deposition of silicon nitride anti-reflection layer on both sides of the structures is followed by the formation of electrical contacts on both sides through the co-firing of screen-printed metallic pasts. The elaborated structures P plus P and plus were characterized by different technique, 4 points, Hall effect, secondary ion mass spectroscopy, and sans VOC. The picture here shows an example of prepared sample, a set of prepared samples. The obtained results will be presented and discussed in the following. So, analysis by Sims technique allows the determination of the depth profiles of phosphorus and boron in silicon, and therefore allows the determination of the dopant concentration in the surface as well as the depth of the junctions N plus P and P plus P. This figure illustrates an example of P and B profiles found for the sample elaborated at the co-diffusion temperature of 960 degrees, where we can see that the surface concentration and the diffusion depth of phosphorus are higher than that of boron. This is due to, of course, the fact that the solubility and the diffusivity of phosphorus in silicon are higher than that of boron. So, we present in figure A here, in the left, the surface concentration of the majority charge carriers obtained by Hall effect as function of the co-diffusion temperatures of phosphorus and boron. It is clear that the increase in diffusion temperature of dopants causes a gradual increment of concentration of surface concentration in the N plus and P plus regions. The increase of the concentration of the surface concentration with temperature is due to the increase of the solubility and the solubility of dopant during their diffusion. The depth of the N plus P and P plus P junctions affect the sheet resistance of N plus and P plus regions. In addition, increasing the surface concentration provokes further decreases in the sheet resistance of the diffused region, as illustrated in the same figures, part B, in the right side. This finding is a proof that the realization of bifacial structures P plus P and plus with different B junctions, N plus P and P plus P. Let us now show the effect of co-diffusion temperature on electrical characteristics of the prepared bifacial structures. We present here the variation of short circuit current density in the left and the open circuit voltage VOC in the right as a function of the co-diffusion temperature. One can clearly see that the emitter N plus yields higher current density with VOC more important compared to boron BSF, boron BSF1. So the data shows the presence of the minimum value corresponding to the structures elaborated at 90, 130 degrees. So in this study, the degradation of the current density associated to boron BSF side is mainly due to the resistive losses at the electrical contacts, which have been found very high compared to the losses in the emitter front contacts. So the use of specific silver aluminum alloys passed by researchers working on these topics is very important in order to decrease the contact resistance with P+. From an electrical point of view, the deterioration of the quality of contact between the front and rear sides can be expressed by an increase in the series resistance. Indeed, the findings illustrated in this figure shows an exponential decay of the current density with the increase of apparent series resistance. Series resistance. We have to note that the value of series resistance is directly determined by the Sans VOC techniques. These results demonstrates the detrimental effect of the series resistance on the current delivered by the solar cell during its operation. So the pseudo field factor and the pseudo efficiency of bifacial structures were also measured using the Sans VOC setup. The results are presented in these figures A and B respectively. We observe that measurements carried out by eliminating the front side, I mean emitter, showed higher pseudo field factor compared to those found on the rear side or boron BSF side. We also observe that pseudo efficiency obtained on the boron BSF side are totally decreased compared to the found on the emitter side. The difference in efficiency between the front and the rear sides of the structures gives rise to the notion of bifaciality factor, defined as the ratio of the efficiency measured on the boron BSF side to that of the emitter sides. The variation of this factor versus co-diffusion temperature is illustrated in this figure, where we can show an increase of bifaciality from 22.6 to 52.5% when the co-diffusion temperature varies from 900 to 960 degrees. This increment can be explained by the improvement of boron BSF performance at high temperature, I mean at 916 and 60 degrees. An additional characterization by spectral response allows the determination of internal quantum efficiency, as shown in this figure. The analysis of this spectrum confirm the previous explanation regarding the degradation of electrical contacts. Furthermore, these results provide another information about the losses in the depletion region. So we finish with a conclusion. In this work, a simplified bifacial structure based on P plus P and plus were prepared and characterized. We have studied the feasibility of simultaneous phosphorus and boron diffusion. The co-diffusion step was performed at different temperatures, and the bifacial structures was characterized by various techniques to determine their electrical and optical parameters as a function of the co-diffusion temperature. Secondary ion mass spectroscopy microanalysis confirms the simultaneous diffusion of phosphorus and boron in both sides of the silicon wafers, creating the emitter Amorphous and the boron BSF, respectively. Additional characterization by using 4-point probe and Hall effect techniques led us to deduce that the decrease in the emitter Amorphous and the boron BSF sheet resistances with the co-diffusion temperature is due to the increment in the surface concentration of active dopant and or the increment of the junction depth. By measuring the current density versus voltage curves, the studied structures showed different behavior according to the co-diffusion temperature. Indeed, the structure prepared at 930 degrees demonstrated a clear degradation in its electrical characteristics. The results has been explained by the electrical losses in emitter and boron BSF, especially through the detrimental impact of the series resistance. The best efficiency was found for structures co-diffused at 900 degrees with eliminated emitter, while the higher efficiency found on boron BSF side was obtained for fabricated at 960 degrees. So the outlook of this work can be abstracted in the following. After this study of feasibility and diagnosis done on the P plus P and plus structures, it remains to reduce the power losses through the improvement of the properties of the emitter and the boron BSF, as well as the electrical contacts. So thank you for your attention.
Okay, thank you, Nabil, for the presentation. Are you hearing us, Nabil?
Yeah, I'm here.
Okay, thank you for the presentation.
I hear you.
Yeah, okay, I have a very short question. Thank you for the presentation. I have a very short presentation. You have shown SIMS profiles of the doping. You measured the doping profile by SIMS.
Yeah.
It seems that you have successfully introduced phosphorus and boron atoms into the system. However, we don't know the activation of these atoms. Do you have any data about the percentage of the activation you have reached in these samples? I mean, are all those boron and phosphorus atoms active that generates the desired electronic functions?
Sorry, I didn't hear very well your question.
Your dopants, are they active? Are all of them active?
Yeah, we didn't carry out the measurement of active dopant.
Okay. So if you wish, we can do some ECV measurements on your samples if you send them to us. Nabil, are you with us? Okay.
Hi. Hello.
Hey.
Hi.
Hi, Nabil. Yeah.
Yeah. If I understand your question, you ask me about the measurement of profiles by ECV.
Yeah, that's right.
Exactly. We didn't make this measurement, but we used the Hall effect to calculate or
Okay.
measure, to measure the majority carrier.
Okay, so you know them, you have active dopants.
Yeah, we didn't make it.
Okay.
We did.
Okay, Nabil, thank you very much for your contribution. I hope to see you later. We hope that you can visit us later, and maybe we can generate some project together with you in the near future. Okay, well, I will present. Thank you.
Yeah, thank you. Thank you.
I will present the next and the last presenters of this session. Gence Bektaş. Gence is a PhD student at Günam. He is working with our implanter. He's an implanter guy at Günam. He has done a lot of very nice studies on implantation process for the solar cell application. So let us hear what he has achieved in the last period of his PhD studies. Okay, Gence, go ahead, please.
Thank you, Professor Turan. I will be listening to my pre-recorded video as well. Hello and welcome to my presentation. My name is Gence Bektaş. Today I will tell you how to simplify process flow for the fabrication of PERC solar cells with ion implanted emitter. Let me start with a very brief story of ion implanted solar cells, which dates back to the 1980s. At that time, 15% power conversion efficiency was achieved on a 2 by 2 centimeter square solar cell. Another important step was the development of solar ion implanter system with throughput of 1,000 wafers per hour. And they showed 18.5 conversion efficiency with this system. Today, ion implantation is used for various solar cell studies, such as interdigitated back contact, bifacial, and tunnel oxide passivated contact. Now, I would like to turn to ion implantation process itself. The definition, we can say it's a controllable way of introducing dopant into substrate. In the process, we extract, accelerate, and direct the ionized atoms into the substrate, which is silicon in this case, under electric and magnetic fields. As we can understand from the definition, it is a physical doping method. Actually, there are a lot of advantages of this method, but I would like to highlight two of them here. Firstly, it enables very uniform doping over a full-size wafer. Secondly, it reduces the number of process steps and complexity by allowing to create any desired pattern and single-site doping. Furthermore, at the end of the process, there will be no dopant glass formation. This is important because dopant glasses such as PSG and BSG are not always very easy to remove from the surface. Here you see a process flow of a PERC cell with diffused emitter and aluminum nitride rear passivation step. The process starts with the texturing and cleaning steps, followed by phosphorus diffusion. Since phosphorus diffusion results in N+ formation at both sides, both surfaces, a single-side etching process is needed to remove N+ from the rear side. The single-side etching can be eliminated from the flow if we apply an implantation method, because it allows single-side doping. The rest of the process flow will be the passivation of rear side with aluminum nitride and anti-reflective coating at the front side and laser contact openings at the rear side. And finally, we perform metallization and firing processes. This is an accomplished ion implanted PERK solar cell study conducted in ISFH. It seems to be a proof of concept study to show the quality of an implanted emitter because they included two additional process steps here. One of them is the deposition of rear protection layer, and the second one is the removal of this layer. They included these steps because they introduced oxygen during the activation of phosphorus dopants. And this oxygen results in silicon dioxide growing at the front side. They did it because it provides a superior passivation at the front side. However, we know that silicon dioxide and nitride rear passivation is very sensitive to rear surface roughness and surface preparation. Therefore, they added these two process steps to avoid silicon dioxide formation at the rear side. Additionally, their fill factor values is not very high. This can be due to a thick silicon dioxide formation at the front side. This is another impressive implanted PERK cell study conducted by Canadian Solar, and they reported more than 20% conversion efficiency. Their aim was to combine silicon dioxide grown during the post-implantation annealing and a thin ALD alumina layer at the rear side. But they also included a rear side polishing step here, because from the previous slide we know that the surface morphology is very effective in determining the silicon dioxide passivation quality at the rear side. Their fill factor, when you look at the fill factor values, it is also not very high as in the previous case. This can be also due to the thick silicon dioxide layer at the front side. So what is our motivation in this study? We would like to eliminate oxygen flow during the dopant activation to prevent silicon dioxide growing at the front and rear side. Because when we do not have silicon dioxide at the front side, the contact resistance of silver to emitter will be low. Also, since silicon dioxide limits the morphology choice at the rear side, we will be more flexible in terms of rear side processing at the absence of, and in the absence of silicon dioxide at the rear side. Lastly, the passivation of N+ with only nitride instead of silicon dioxide and nitride stack will lead to progression of other type of silicon implanted silicon solar cells, such as N-PERD and IBC. For example, N-PERD solar cells, bifacial N-PERD solar cells, have P+ emitter at the front side, and alumina and nitride stack provide a superior passivation on P+ emitter. If we have silicon dioxide at the P+, then the passivation quality of alumina and nitride stack will diminish. It is the same for IBC solar cells. When we have front floating emitter at the front side, silicon dioxide may diminish the effectiveness of aluminum nitride passivation stack at the front side. And this is our process flow to fabricate ion implanted solar cell. We also start with texturing and cleaning processes. Unlike the others, we do not have rear side processing step, and we do ion implantation and activation of dopants and do HF fitting just to ensure that there will be no oxide growing at the rear side. And rear side is passivated with aluminum nitride stack. Front side is coated with anti-reflective coating silicon nitride, and laser contact openings are performed. Finally, metallization and firing processes are conducted. Here you see the doping implantation parameters. We apply 2 doses in our cells that you will see in the coming slides. This D1 and D2 are corresponding to doses, and the sheet resistance were measured by 4-point probe as 81 and 57 respectively, and their corresponding doping profile curves are given on the right side. It was measured by ECV method, electrochemical capacitance voltage. Of course, the higher dose results in a deeper junction and higher peak concentration at the surface. Before cell fabrication, we also investigate the effect of firing temperature on implant use of phosphorus implanted wafers. For this, we fabricated symmetrical samples, as you see in the figure here. The samples were implanted with dose of D1, the lower dose, by ion implantation system, Bosphorus ion implantation system in Yunan. Then PCVD nitride was deposited at both sides. The samples were fired by a conveyor belt furnace to release hydrogen from the silicon nitride. The output of this experiment was very interesting because the typical firing temperatures around, let's say, between 750 and 800 are very detrimental to implanted emitter. But when you decrease the firing temperature, the implied VOC is improving for the implanted emitter. For these firing temperature, we also check the contact resistivities. In contact resistivity experiments, we applied 2 doses, D1 and D2, also 2 firing temperature. The contact resistivity measurements were conducted by TLM method. The results show that the contact resistivity decreases with increasing fire temperature and increasing dose, as expected. Although firing temperature slightly affect the contact resistivity of high dose, you can see from red to blue, it is more significant in the case of lower dose. Increasing firing temperature results in decreasing, increase in firing peak temperature results in decrease in contact resistivity. And this is the cell results of our PERK cells. Our champion cell showed 19.97 power conversion efficiency, which is comparable to the ones in the literature. And our fill factor is 80.61. If we look at VOC values, this is interesting, of course, because the firing temperature has a very strong effect on VOC values. For higher firing temperatures, the VOC is lower, but for the low firing temperatures, the VOC is higher. But still, for the lower firing peak temperatures, we have high fill factor values. And if you look at the EQ graphs on the right side here, the cell response to photons with short wavelengths are similar for diffused and implanted emitter, especially for D1. If you look at blue and black curves, the blue is standing for D1 and black is standing for diffused emitter with sheet resistance of 1 ohm square. They are almost very close. D2 is a little lower because it has, the doping concentration is very high for the case of D2. In the summary, we can say with its simplified process flow, we obtained 19.7 power conversion efficiency on implanted PERK cells, which is comparable to the ones in the literature. We also showed the effect of firing temperature on implied VOC of the emitter and the contact resistivity of silver to emitter. Finally, we achieved fill factor of 80.61 for implanted PERK cell, which is higher than the ones in the literature. And this is my references. Thank you for listening to my presentation.
Okay, Genji, thank you very much for this nice presentation, showing us that implanter might be a good alternative to the existing technologies.
Thank you.
I have one question. Maybe there are more. Okay. My question is about the losses that you have. The short circuit current seems to be low compared to the high efficiency solar cells. And what is the main reason for this low short circuit current value in your case? What do you think it is?
First of all, can you hear me? Yeah.
In order to reach 23% from your cells. This is next question.
Yeah. First of all, can you hear me? Because at the beginning, I think my voice didn't
We
reach
hear
you.
you very well.
Okay, thank you. First of all, we didn't analyze the cell, I mean, very in detail. Maybe the main loss in JS is coming from the rear side because it's texture, it's textured surface, and there should be some optical losses when it's you know, polished. There will be some reflection from the rear side, and it's gonna increase the JC a little bit more. But our aim here is not to achieve very high efficient PERC cells, but we want this implanted PERC cell to pave the way for other technologies such as IBC and maybe TOPCon IBC combination, and so on and so forth. What was the other question?
What do you need to do to reach 23%?
With PERC, implanted PERC?
Yeah, implanted PERC.
Tough question. As I said, it's not our main purpose, but we can also mimic the diffused PERC cells at the rear side, first of all, and we should reduce the doping level at the front side because the dopant concentration is very high due to some reasons. Yeah, that's my answer to this question.
Is there any other question? I think there is no other question, so we are already behind the schedule. Thank you very much for your presentation. For everybody presented in this session, I am very happy to hear that we and the others have made a lot of progress in the PV science and technology. And I close this session now. The next session will start at 2 p.m. with the keynote speaker from ISFH, Robbie Papes. So please join us at exactly 2 p.m. Thank you.